So in this particle in B01, data management, we're going to look at this part um cleaning our own data in using spreadsheet data. So that's our focus here. So as we know from the videos earlier, we want to separate our raw data from our clean data. You may have multiple cleaning steps, so this may take a few steps to get here to where you have fully cleaned data, but it's worth having different versions of your data so you can check what happened on the way and ensure quality and integrity at each step. And then you may have several different analysis to do, and therefore you may have different your data set split into different versions of those analysis, which is fine. Ideally, I just actually have the clean data and you feed that into R with code and you analyze it, and that's what we're going to do. So what we want to do is create a data dictionary for our data, create a detailed data cleaning plan using the data dictionary, import the data set into R, visualizing support there, do manipulation with code not manually. So we're going to look at how we get used to using R for this process. We talked about how do you create a data dictionary already, and that's something that we looked at earlier. So we want to learn R because without it, we can't see very far, and it can be frustrating when you're not able to do what you want to do. So learning about that, better approaches that can allow us to do much more efficiently will mean that we're better scientists, although it does take a bit of learning at the start. And then what's nice is that we can pass on our knowledge to others. So what we're going to do is log on to our studio server at this website. You should have a login name and password already. We're going to use these RMD files, which are our markdown files, which are like text files, which allow us to write code. You can record your commands, which are inside your RMD file. You can also record other things in a ELN, but don't use a Word document or something like that. And you can use Excel, but just to store raw data as CSV if you're using structured data, but don't store it in any kind of Excel format because that will make it very, very hard to look at it properly. So we're going to use this RMD files. A vector is a list of numbers or a list of strings as well. We can define a variable from vectors, such as x, and then we have functions which is R code that does something such as the mean of x. We get the function takes the argument x and calculates the mean of those set of values. So if values are 1, 2, 3, 4, 5, it'll return the value 3 as the mean of those numbers. An argument is something required by our function, such as x above. Some functions require more than one argument. A library is a package of R functions that does something specific, and it's loaded with the library function. We'll also have the function install.packages, which allows us to install packages, which is very useful. Our environment is a workspace that we're working in, and unfortunately we're using Windows here, but more proficient people will use Mac or other types of computer systems. And then we're using CRAN. So CRAN is our repository containing lots of useful libraries that we can download. Another repository is called Bioconductor, which again contains lots and lots of libraries that we can use. So when you launch RStudio, it will look like this. So you can see there'll be code up here where you write your code, you script it, and you hit the run key up here. And that will mean that it's executed down here in the console. So you can see this code output here, and you see this greater than a symbol down the bottom. That's where the code goes. So we don't actually write code down here. We write it up here, execute it, and it's sent down here. This is our environment and other features that are up here, which just tell us what we've been doing. So we can track our processes. And then on the bottom right, we have a series of tabs where we can do things like plots. So you can see here, there's a plot of some random numbers. There's also a files tab for reading in local files, a packages tab for reading in packages, a help tab for finding getting help, and a viewer tab, which you probably won't use very much. So there's a few things we can do as well. We can make sure that these two things are shown here are off, so that we go to tools in the menu, go to global options, which is the drop down of tools. Then we go to the R markdown pink button option here, and turn off show output in line for R code chunks, and show output in line for all markdown documents. Turn those both off, because that will make it easier to read in simple terms. For installing packages, we click on this packages tab, we will by default install from CRAN. We type in our package name here, lowercase, and that's installed to a library location. Other things that are new, if you haven't done R before, we can assign variables. So we got X is pointed to by Y. So this is a greater than symbol, then a hyphen. So that symbolizes that X becomes the value 1.5. So the thing that we're assigning it to is on the left, and the value we want to assign to the variable X is on the right. If we switch it around, that will create an error. In the same way, if we want to assign Y the value of 2.6, we have Y on the left and 2.6 on the right. We have standard operators, so R can act like a calculator, and we can have A to the power B or A modulo B. That means getting the remainder. And we can do calculations like you would do with a calculator. Spaces don't matter, so you can have A plus B without spaces and A space plus B, or lots of spaces, or we'll kind of figure it out. It doesn't matter how many spaces you use. We can create vectors and they're sets of numbers in this instance. So use the concatenate function to achieve that. So X is assigned the concatenation of nothing here, there's no numbers. But if you do X is assigned the concatenation of 1, 2, 4, and 8, I'll create the vectors of the numbers 1, 2, 4, and 8. Vectors can also exist as strings separately from numbers. So we don't want to mix numbers and strings because that's just confusing. In the same way, we don't want to mix spreadsheet columns with numbers and strings. So if we have, for example, a set of strings here, X is black and white, and you ask the type of X, it will say that it's a character, which is different from numeric. If we say Y is the numbers from 1 to 10, this will tell us that Y is an integer. If we assign the X the values of 11, green, and 33, this is our wrong approach of using strings and numbers, and get the type of Z, it'll be a character. And if we get the type of Z for element 1, which refers to element at the value 11 only, it will still call it a character because green is a string, and therefore everything is assigned as a string. If we get the type, if we turn Z element 3, which it was 33, that will return a number because we're converting it to numeric, or we can convert it to an integer as well, and that will assign us as an integer, and we can turn it back from a numeric data into a character as well, and that will create it as a character. So therefore, we can use these functions to create something as numeric in case it is not read in as a number, as a character, which is like having a label, as a data frame, make something into a table, is NA. We can check if something is NA and it returns true if it is NA, or false if it is not NA, and length gives us the length of the array. So this kind of cartoon summarizes that. We can have numbers like 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. All of these are numerical, but if we include something in quotes, that will be a string, and everything will transform into being a string type instead of being a mixed bunch of variables there. So we can create long vectors like this and perform manipulations such as getting unique values, sorting, getting unique values. So you can imagine that if you have a long vector, that can be useful. We can also use the iris dataset as an example of tabular data. So the iris dataset, you can see this relatively simple data with sepal length, sepal width, petal length, petal width, and the species. And then we can use these square brackets to extract certain elements across the rows and then the columns. So this 1 to 5 with a comma and nothing means that it selects all the columns. Whereas this one here, we select just the first 2 columns, sepal length and sepal width, which are the same as these ones above. And we're looking at rows 1 to 5. So if we had no rows there, I just had iris like that. And then square brackets, the comma, and 1, 2. That would mean that we get all the rows that are present. What else can we do? So what we can do is, for example, use options to turn all the digits to be rounded to 3. We can fetch the data iris, check the number of rows, check the number of columns, check the dimensions, check the column names, which is very useful. So we know what are the variable names that are present. And then we can use this function called subset, which is very, very convenient. For selecting from iris, just to say we want to get all the columns except species, that will be a minus that ignores the species column and returns all those columns except we're giving that to the function head next. So it only returns the first 6 rows of them. And we'll look at an example of this later. We'll also use this function data frame. So data frame is very, very useful for creating a structured data set. So if a vector, say here, of heights and weights, we want to link it together, and we want to link it together such that the height 150 is corresponded to 65, 170 to 70, 168 to 72, and so on and so on. And we can do that using the function data frame with weights equals W, heights equals H. So H and W take on the values inside the table. So it looks something like this. So we get our patient data, what's inside there. So we see we have a bunch of heights and weights inside there, and such that the first person is the first row, 65 and 150. So in the same way as mentioned before for iris, we can access the row information across I and the column information as well. So this would give us all the values in row 2, for example, if I equals 2, and this would give us all the values in column 3 if I is equal to 3. And you can try some of these yourselves. You can try to create a new data frame from your own heights and weights or these ones above, and use summary to view the contents. So summary command is useful. It just takes on the data, our data as an argument, and then we have the function. Subset, as mentioned, is a useful command. You can get help in that by putting a question mark and then subset afterwards, or you can search for information on it online. We're going to use a data set air quality for that and look at the structure of it first to get a feel for what's inside the data set, because we don't know at the start. So that's a very good way of getting an understanding of what. It also tells us what's the data types inside each column. We get a summary to give us a numerical summary of these things. So if you're checking the quality of your data, summary is a very handy command to get a sense of what's going on. And we can subset air quality, for example, for the warmer temperatures to extract that particular set of data. So what we can do is focus on key commands that are useful, such as length. So that gets the number of entries in a vector. So that could be one vector. We have data frame to make a table. Factor creates labels to write a data frame. Summary is mentioned already. And list. A list is like a multi-dimensional array. It's great for semi-structured data, or indeed some types of structured data, but data frames are more useful. And a handy command if you need to unlist to delist things is the function unlist. There's other examples of data sets that are inbuilt into R and the Davis dataset. There's also a dataset of the Titanic. Contains a bunch of people's sex, height, weight, reported weight, and reported height. And you can get the structure of Davis, glimpse the parts of Davis, get a summary of Davis as well, in the same way as you might for any set of data. And what you're going to do then is take this function that's given to you, read.csv for your data, and import your data in there and try to assess key features of it, like look at a small portion of it, look at the head, the dimensions, number of rows, columns, and structure. What you might need to do as well is wrap a data frame function around this read.csv function to read that in more effectively. You may come across errors, and that can happen. So here we have the read.csv function and the file here, and then the data frame function wrapped around it. If you get this error message saying cannot open file, no such file or directory, error in file, cannot open the connection, this means the probably is you're not in the right folder. And we'll look at that in practical as well. And then we have our second part here. We have data frame read.csv for file choose. This is a nice way of manually selecting the file. It's probably easier way if you're new to it. Another key component of data cleaning is visualizing it. So we can plot, for example, if we have a bunch of heights in our data frame, $X heights, we can plot them in that way. We can do a histogram of the heights, do density plots of the heights as shown here, do a box plot of the heights as shown over there as well. What we're going to do is set our working directory. So we've got the ndrive public omics and learning B01 lab 1. We're going to install this package called reader, which allows us to use this function read underscore CSV, our example data. We're going to import that as a data frame and view it. And if you do that, you'll get this small set of data, very small table. We've got 4 samples, some lengths and widths, and you see there's some NAs in there as well, which is typical in normal data. And what would be nice is if you apply these functions to that data set and then your own data set. So you have class, type of, structure, dimension, head, tail, names, and view. More handy ones for assessing data quality include summary, plot, is NA, duplicated. So these might apply more to individual vectors, min, max, and range. And what we're going to do is install tidyr and gather x. So we're going to call it as a new variable, new one. We're going to create the key and value as year and value. And then we're going to perform the operations on columns. The columns contain our numerical data, which are columns 3 and 4, such that each row contains a single numerical data only. So what we'll get at the end is a table like this where we have a sample, the state, the replicate, and the length, and that corresponds to the value 11. So you can see we have lengths and widths. So this column here is lengths and widths, and these correspond to the different values that are present. So it's only one value, and it's a long form of data instead of the wide. What we can do then is take a linked data set called linked data.csv, read it in the same way, check the structure, install this package called dplyr, and then what we're going to use is this function called inner join to join x and the linked data. So we know the data is linked because they contain the same sample names, A, B, C, D. So the linked data, as you might notice here, contains additional information that's not in our original data set. So it says if it's been imaged, the cell line, and the intensity. So this inner join function allows us to merge these data sets. So that's a very simple example of data integration. So the purpose of this is to show you how you can take data sets, assess them, and integrate them as well. So let's look at how we can do that in our studio next. What we did mention there is that, and we'll mention in the very practical itself, is there's a very handy tutorial called Swirl that you can use. So I'll briefly talk about that now. So if you install the package Swirl, this is in our lab 1 file. You can activate that package and run that there. And what we're going to do is actually try this on the RStudio server, I should have mentioned. So let's take that over there. So to access the server, we just go to the website link, 149.155.250.13.87.87. You should have this already. And then we log in using your assigned password and username. You can see I have some stuff already, but we'll just install Swirl first of all. And you can see that the setup is similar to what we had before. So you can see here it's installing different things inside there, and this is normal for package installation. You can see that it's trying to download stuff initially, and it's just checking that everything is there that it needs. You can see there as well that we've all the you can see that that this has worked well, and we can check that if we just check that the package has worked. You can see we can activate the tutorial with the command swirl. So if for the library command here, if that gave us an error, we'd know it didn't install. Call me Tim. And then it just hit enter to continue, press 1 to proceed. Let's go 1 again to start our programming. And you might want to start with the basic building blocks. Just keep hitting 1. And then you'll give you feedback on what you need to do. And if you try to do this question and maybe you make a mistake, it'll give you prompts and say, what you're trying to do. And then if you want to exit, I think was it buy? Yeah, so we've exited the tutorial because if we stay inside the tutorial, it's hard for us to do what we wanted to do in this practical. So to load our RMD file, we go to this yellow button here. Our target directory is our home directory, and we choose a file we want to upload, and that's our RMD file in this lab 1 folder. So we open that, hit OK. and then I need to open it. So file, open file. So I have a bunch of files, but lab1 file is the one I want to open. And we have that there. So you can see all the files in my local folder. So we talked about swirl already. We also talked about R as a calculator. So R can do calculations. If I run this command, 10 plus 54, what I'm doing is hitting run here and running the selected lines on which my cursor lies. So you see there's beside 54, I hit run here and it runs the selected lines. You could type 10 plus 54 here, but that's slow and it's nicer to write it up here. So if I want to say do 10 plus 55, I can do that quite easily. And when I run through these lines, I'm actually pressing Control and Enter. So you can see there, it gives us it acts as a calculator, giving us feedback on the calculation that was performed. So you see here at line 48, if we say, what is X? Oh, I had X assigned as something else. If we reassign X as 1.5 and say, what is X? We see that if whatever way we say print X, for example, it's 1.5, show X, X example, it's still at 1.5. If we change X is now 2, X takes on the value 2 and value 1.5 is gone. In the same way, you can assign the value 2.6 to Y and check that. It's 2.6. We can go to our environment tab up here at the top, environment. And if we drag down this gray bar a bit, I have a lot of variables. I see there X and Y are 2 and 2.6 respectively. And then we can do other things like X to the power of 18. And let's try assigning a set of strings and a set of strings and the number 5 to X and see what's the type of X. So X is a character. And if you check what's the type of element for X, element 4 is a character as well, even though if we ask what's inside X4 is the number 5, R sees the number 5 as a string. We can use the C function, create sets of numbers. So if we run this function, concatenate the numbers X, we see 1, 2, 3, 4, and we can access the elements of X. So we can go from elements 1 to 2. We can look at elements 1, 3. We get those exact ones, 1 and 3. And we can rearrange them in different ways, 1, 3, 2, and that'll give us back the corresponding elements. And we can do the same for Y, and that will assign a set of values to Y, and we can even multiply X by Y because they both have 4 elements. And we have Z there. If we do X by Z, that will give us an error because they don't have equal number of elements. Z here is 3 elements, X has 4 elements. That can create an error, and that's why R shows this message. We can then also concatenate things together as well. So concatenate X and Y to create a longer variable called V. So we went through this already. Then we can perform sections inside here. So for example, in V, if we want the elements of V that are greater than 5, we can do the greater than 5 inside the square brackets, and that will select the ones that are greater than 5. If we want the numbers that are less than 3, we can return the values that are less than 3 in that way as well. If we want the values that are equal to 0, you can see that returns nothing because no elements in V correspond to 0. If we want the ones that are not equal to 0, we can also do that as well, not equal to 0, and we'll put another condition, V greater than 1. You see that most of the elements are returned, but not the first one because that was equal to 1. So that's a basic introduction to these aspects. So we had our discussion of tables. So these are vectors of heights and weights, H and W. They're just a set of vectors, and we can link them together using the data frame. So we can do it for one vector only, like the vector, the patient data, which now contains the weights only. And what's nice is that we get the structure of this. So it gives us, say, the structure gives us the it says that it's numerical data and gives us the first few values inside there if it's complex. We get a summary. It's like it's a numerical summary of those heights, which is useful if you're looking at complex data with many dimensions and you want to check that it actually makes sense. And we can also visualize it just doing view and patient, oh dear, patient data, and that will appear as a tab so we can see it individually. We can also look at iris, and then, as I mentioned before, we can do the head and get the parts of iris. If you view, oh here, view iris, you can see there it contains a big table like this. And then if we select, so we're subsetting iris and selecting minus species. So for example, if we select just the species only, we'll see just that column was returned. So you can see there we just have the species only and none of the other data. So we're selecting minus species, which gives us everything else. So we have the first 4 columns only. And then if we do head or say tail of species, we just get 6 columns. Tail gives just the last 6 columns. You can see we lack species. But then if we just put in tail of iris only, you can see the spot the species will be there. Oops, and we check the number of rows columns of iris, which is handy. So it's 150 rows, 5 columns, 5 by 150, and the column names there are sepal length, sepal width, petal length, petal width, and species. So then we can use the function subset more, and we're going to use air quality here. We don't know what air quality looks like, so use the structure command to look at that. So you can see it has 6 columns: ozone, the solar, wind, temp, month, and day. So, and you see there's NAs inside there's 153 rows and 6 variables. So then we might want to select, say, the temperatures that are greater than 80 degrees. You can see that we have a lot of rows inside there. So let's maybe elevate that over 90, 5. There we just have 2 rows that fit that criteria. So we can perform simple operations in that way. And then as you can see from the example above, we can use the select function to select, say, the ozone column only, if we just want that, and get those values only. And we can create new values, new data frames from this, such as my air1, and look at the structure of my air1. So there you can see we have the different values here present. We have 68 rows out of the 153. And therefore you can try these questions yourself and getting the temperatures greater than 60 and selecting the columns for wind and day. And then if we want to look at Davis, that's another example data set. There's a lot of example data sets. We have to install this package called car. We don't reinstall R. That'll be a lot of work. We just wait for this to install. So after we install the package car, we have to activate it. So install it, you only install it once. And then we activate car. It should be active now, and we can view Davis. That contains a more real data set, so it's 200 entries, reported heights and weights, as well as the heights and weights themselves. We get a head of Davis, a glimpse of Davis, sorry, the structure of Davis. You can see there we have sex as a factor, and they have integers for the heights and weights. And then glimpse is also useful to find out what the data looks like. Summary also, because you can see there the heights and weights, the variation that we have there inside that data set. What we're going to do is set. So if you see here in files, we have our data set here. So we're going to look at our own data set here. And easy way of doing this. So where's the example data set? Oh, I have to upload it. Okay, hit the yellow arrow, choose file, and we're going to upload example.csv in the lab1 folder. So sometimes the upload process is a bit slow. Hit OK. And then we should see that appear there. We're also going to upload while we're at it the linked data that we're going to look at later. Linked data.csv, upload that as well. So you see they're down there. So if you look at view file, we can view what's in example.csv. So you see it's comma separated. And same for linked data, it's also view file, it's also there as well. And a nice way of doing this is we can import this data set. So you hit the import data set, we can view a kind of interface to import this data set in the right way. So it kind of automatically detects what's the delimiter and gives us code there to let us import it. So if we run this thing, then it will automatically call this data example in this case. Here we can just use these functions, so we can activate readers already installed, so you should be able to just hit library reader and then use reader to read in example.csv as x, and you can view what it looks like. So you see we've got 4 samples, they have a state what were infected. There's different replicates, lengths and widths with some NAs. We can ask what's the class of this? It's a data frame. Type of, it's a list. The structure is given there, which we saw. The dimensions, it's 4 by 5. So that's 4 rows and 5 columns. Got head and a tail are the same thing here. And names gives us the column names that are inside there as well. So what we can do is a summary, or we can plot it. So this maybe is not the most sensible way of approaching it. What we can do is probably plot x. What we can do is the $sign to plot the lengths. Oh, whoops. Plot x $length. You can see the lengths. There's only a few values that are valid. We can do get an emergent summary there. So you can see there for sample state and replicate, these are not meaningful, whereas for length and width, these are meaningful. That gives us a sense of what's present, including NAs as well. Is NA, so that will mean we can see there we have 2 NAs, they're true in parts of the table. We can check across the rows if any are duplicate, they're false. Any duplicate, no. Unique elements, we see all 4 rows are unique. NA omit, so you can see if you do NA omit, it omits any rows with an NA anywhere. See, rows 3 and 4 are completely gone. So NA.omit can be used in certain circumstances, but may not be always wise depending on the nature of the data set we're trying to look at. Next, what we can do is convert this. This is wide data. We can convert it into long data with the function tidy, the package tidyr. And what we have here is a function called gather. We're gathering x, and we're using the key. Maybe that's the, what we want to call that, the parameter. We have the value, and this last thing here, our 4th argument, is the numerical data that's of interest. So we're giving that's what we give at the end. And we're going to call this data frame new1. So if we run this, no. And then we check what new1 is. You can see there now we have ABCD twice. Everything is repeated twice, and the lengths and widths are in separate rows. This is the long data format, it's not wide data. And you can see that this is 8 rows instead of 4 rows, and is a different format. And this is long data, which can sometimes be easier for subselecting or manipulating data or checking data. What we're going to do finally, as a final thing, is import the linked data in the same way and check the structure of it. So we see there, if we view the linked data. Oh, sorry, it's view linked. We have our linked data, but the sample names are the same. Then we have the cell line, replicate intensity, and imaged. So to link those 2 data sets together, we can use the dplyr package and use its function inner join names to join x and linked together. So if we look at inner join names, because we have 4 samples are all the same, which is easy, that's a straightforward join. If, for example, we had our linked data set where we just had 3 rows only, let's call it linked 2. You can see there we got 3 rows only, and we did an inner join of these together. That would mean that we actually lose 1 row. So only the ones that can be joined are listed here. So inner join is more complex than this, depending on our data. If we're dealing with real data sets where things are a bit more heterogeneous, you can see here that linking data sets together with R is possible. So if you have any questions on this, we can cover it in the class itself, or you can even let me know in advance. And please bring your own data sets so we can evaluate them there.